Good afternoon, everyone. I'm Renee Smith with Virtus Nutrition and the host of the Fatty Acid Forum. Welcome to our fifth webinar in this series entitled Dietary Fat Supplements and Body Condition, Does Fatty Acid Profile Matter? By Dr. Jim Drackley of the University of Illinois. We at Virtus Nutrition believe that fatty acids matter. While fat typically makes up a small percentage of the diet, the impact fatty acids have on production, cow health, and dairy profitability are tremendous. It is now my pleasure to introduce you today to our featured contributor, Dr. Jim Drackley, Professor of Animal Sciences at the University of Illinois at Urbana-Champaign. Dr. Drackley received his PhD in nutritional physiology from Iowa State University. Since joining the faculty of the University of Illinois in 1989, his research program has focused on nutrition and metabolism of dairy cows during the transition from pregnancy to lactation, lipid, fat utilization and metabolism, and the aspects of calf nutrition and management. Dr. Drackley has published extensively, has trained 36 graduate students, has received numerous professional awards, and is widely sought by the industry for speaking and consulting. With that, I would like to welcome Dr. Drackley to lead this discussion on dietary fat supplements and body condition. As a reminder, please feel free to type any questions you have into the box in the lower right-hand corner of your screen during the webinar, and Dr. Drackley will address those questions at the end. Thank you, and now here's Dr. Drackley.
Thank you, and good afternoon, everybody. It's my pleasure to join the Virtus Fatty Acid Forum series. Today we're going to discuss whether the composition of dietary fat supplements affects body condition, and specifically the question that we'll ask is how does the balance of the major energy-related long-chain fatty acids in dairy cows affect body condition and milk fat as well as milk production? And we're speaking today mainly of the fatty acids palmitic, stearic, and oleic, C16, C18, and C18-1. These are the fatty acids in greatest abundance in the composition of many of the commercial fat supplements. Before we begin the discussion of the topic, it's important to understand how fatty acids are absorbed from the small intestine. You'll recall that in the rumen, most of the dietary fatty acids are hydrogenated, become saturated, and that's what reaches the small intestine for absorption. Within the small intestine, these fatty acids are emulsified by the bile salts and form micelles with the help of lysolecithin. The fatty acids then are absorbed into the intestinal cells, reconverted to triglycerides, and packaged into triglyceride-rich lipoproteins, which we'll abbreviate throughout as TGLP, that are similar to very low-density lipoproteins. The TGLP enter the lymph system and then provide dietary fatty acids to various tissues such as the heart, the muscle, adipose, and mammary gland. Dietary fats bypass the liver for the most part. The major fates then of the dietary fatty acids throughout the body will be one of these. They can be either oxidized to carbon dioxide for energy, they can be deposited into body fat, triglycerides in the adipose tissue, or they may go into intermediate triglyceride pools such as in the liver and muscle. Or the other major fate is to be secreted in milk fat. The metabolic fate of the dietary fatty acids will depend on the tissue that we're talking about and the physiological state of the animal. To illustrate the effect of the physiological state, we'll use this diagram that shows the adipose tissue, the liver, and the mammary gland. For a cow in a healthy, well-fed state and positive energy balance, feed intake will supply most of the nutrients that the cow needs, with propionate from rumen fermentation being converted by the liver to glucose, which will go to the mammary gland and drive milk synthesis. The fatty acids from the diet that are absorbed and converted to triglyceride-rich lipoproteins will be absorbed and distributed to the mammary gland for milk fat synthesis, and also the fatty acids will be used by adipose tissue for fat storage. If we transition then to a cow in negative energy balance, the situation becomes a bit different. Now feed intake is insufficient to supply the propionate and other nutrients that the cow needs, and so amino acids, glycerol, will be used along with propionate to make glucose for milk production. The dietary fatty acids that are absorbed as TGLP will now be used primarily by the mammary gland because the adipose tissue is mobilizing stored fat rather than taking up additional fat. Some of the TGLP in both cases will be used by tissues like the skeletal muscle and the heart as an energy source, and this doesn't change greatly between physiological states. So to summarize, in positive energy balance, dietary fatty acids will be mainly used for oxidation to provide energy, will be deposited in body fat, or will be secreted in milk fat. In negative energy balance, the dietary fatty acids will be used as fuel sources or will be secreted into milk fat. In ruminants such as dairy cows, the oxidation of long-chain fatty acids, whether from the diet or mobilized non-esterified fatty acids, is somewhat limited. Estimates have shown that direct oxidation of long-chain fatty acids supplies only 6 to 12% of the cow's total energy. So for a 600 kilogram cow at 30 kilograms of milk per day, this ranges from 230 grams of fatty acid oxidized for a cow in energy balance to as much as 500 grams per day when in negative energy balance. This is less dependence or less ability to oxidize long-chain fatty acids for energy than in non-ruminant species. Now let's switch to the mammary gland and talk about the source of milk fat. The fatty acids that go into milk fat arise from two different sources. First of all, they can be synthesized de novo in the mammary gland. This will be the fatty acids of carbon chain lengths 4 to about 14 plus half of the C16 fatty acids. These fatty acids are synthesized within the mammary cells primarily from acetate from rumen fermentation. Beta-hydroxybutyrate, or BHBA, also can be used as a primer for the first 4 carbons of these fatty acid chains. The other source of fatty acids for milk fat is from uptake of preformed fatty acids from the blood. This supplies the other half of C16 fatty acids and all of the C18 or greater length fatty acids. These fatty acids are either absorbed directly from the digestive tract or will be mobilized from body fat. If we look at the changes in fatty acids within the body of the cow from the blood triglyceride lipoproteins to milk fat or adipose tissue, it's instructive to look at the differences in these fatty acids that make up the fats here. First of all, we'll see in milk fat that there's quite a large quantity of the short and medium chain fatty acids that again are made within the mammary gland. There are almost none of these within adipose tissue or circulating as part of the blood TGLP. In contrast, blood triglycerides are very highly enriched in stearic acid, C18-0, which directly reflects the composition of the fatty acids that are being absorbed from the small intestine. As those lipoproteins are circulated to the other tissues, however, there are changes in stearic acid content. You can see much lower content of stearic acid in both milk fat and adipose tissue, with higher amounts of C18-1. Mammary and adipose tissue have the ability to desaturate stearic acid or convert it back to oleic acid. This is important to maintain fluidity of the fat within adipose tissue or milk fat. The adipose tissue synthesizes only up to 16 carbon fatty acids and then elongates that by 2 carbons to 18-0 or stearic acid, which may then be desaturated to oleic acid. So if we look again at the changes from the blood to the various tissues, another striking difference is the change in the ratio of 16 to 18 carbon fatty acids. In the blood, there's a very low ratio of 16 to 18 carbon fatty acids compared with the mammary gland and adipose tissue. So there are marked changes here between the blood triglycerides and the profile that will be secreted in milk fat or stored in adipose tissue. So to summarize that, blood triglyceride generally will reflect the fatty acid profile of the fatty acids absorbed from the duodenum or that reach the duodenum for absorption in the small intestine. Blood triglycerides are higher in stearic acid than adipose fat or milk fat. Adipose tissue triglycerides are higher in oleic acids than milk fat. And there's an increasing ratio of C16 to C18 fatty acids from the blood to the adipose tissue to milk fat. Now, does this matter to the cow in terms of the response to dietary fat supplements? Let's look at the effects of C18 versus C16 fatty acids in the diet. There's quite a long history of the fates of these different fatty acids in cows. We'll start first with a very nice in vitro set of studies that was conducted with mammary tissue slices or mammary cell preparations from goats and cows. The left-hand graph here shows the incorporation and secretion of de novo fatty acids by mammary slices. And this shows the effect of added palmitic acid in the blue, oleic acid in the red, or stearic acid in the green. When palmitic was added to the in vitro preparations of the mammary cells, the output, synthesis and output of the de novo synthesized fatty acids was greatly increased. With oleic supplied to the in vitro medium, there was really very little effect. And with stearic acid added, there was actually a slight inhibitory effect. The panel on the right shows the incorporation of those added long-chain fatty acids into fat by the mammary cell preparations. Here again, palmitic acid is used much more readily for incorporation into the milk triglycerides than the other two fatty acids, oleic or stearic acid. An older study from England showed the effects of a series of saturated fatty acid mixtures supplemented to cows. In this case, the researchers added C14, C16, or C18 to the diet of cows and measured the effects on production and milk fat composition. You'll see that when muriatic acid or C14 was added to the diet, there was no effect on milk fat yield, but palmitic acid greatly increased milk fat yield. Stearic acid caused a smaller increase in milk fat yield. Palmitic acid was able to increase milk fat content without decreasing milk yield, whereas C14 had a marked negative effect on milk production even though milk fat content increased. The fatty acid profile of the milk fat reflected these dietary changes. When C14 was supplemented to the diet, there was a large increase in the C14 content of milk fat with decreases in the other long-chain fatty acids. When palmitic acid was supplemented, there was a large increase in palmitate concentration of milk fat with, again, changes in the other fatty acids. Stearic acid caused an increase in stearic acid in milk fat and also oleic acid in milk fat, again because of the desaturation ability of the mammary gland. The milk fat yields, fatty acid yields in grams per day showed similar trends. C14 increased the C14 yield in milk fat. C16 increased the C16 yield. And stearic acid or C18 increased the C18 yield as well as the C18-1 yield. Another way to look at this is by directly infusing fatty acids into the abomasum or the small intestine of the cow to avoid the effects of rumen biohydrogenation. In this study from our research program many years ago now, we infused a mixture of saturated fatty acids that supplied approximately equal portions of palmitate and stearic acid. If we look at the milk fat fatty acids relative to the control cows that were not infused, we see there was an increase in yield of both palmitate and stearic acid or stearic acid plus oleic acid. The increase in these milk fatty acids secreted was about 22% of the total amount of those fatty acids that were infused into the abomasum. A French study showed similar effects when they infused relatively pure mixtures of palmitate or stearic acid into the duodenum. When the researchers infused palmitate into the duodenum, there was a substantial increase in milk palmitate output over the controls. When they infused stearic acid into the duodenum, there were smaller increases in the stearic and oleic secretion in milk fat. The relative transfer then of palmitate into milk fat was almost 50%, whereas for the 18-0, the incorporation into milk fat was much lower. Now if we look at some more recent feeding studies, this was an Idaho study that supplemented a mostly C16 fatty acid supplement in increasing amounts to the diet from 0.5 to 1.5 kilos per day. Milk yield was increased by any of the amounts of the fat supplement, and milk fat percentage also was increased. A study in California showed, again looking at a high 16-0 fat supplement, showed a small increase in milk production for the supplemented cows relative to unsupplemented controls. However, this increase was confined mainly to the lower producing cows as they divided them out retrospectively. In contrast to the other studies we've looked at, milk fat content was not increased by the C16 supplement in this study. Overall, though, if we look at the body of research data available, it seems that high palmitic acid supplements can modestly increase milk fat content and output, at least under some circumstances. C16-0 does seem to be transferred into milk fat with greater efficiency, as we've seen from both in vitro and in vivo effects. But it should be remembered by simple thermodynamics that if we transfer more of the fatty acids into milk fat, there will be less available for other functions in the cow, such as oxidation for energy or to restore body fat reserves. Now, as we move on to the next segment of the webinar, I'd like to show you some of our data that I've used to try to interpret or understand changes in fatty acid metabolism relative to our question today over an entire lactation cycle. I've looked at fatty acid balance here to evaluate changes over the lactation cycle. And fatty acid balance is simply the digestible fatty acid intake minus the fatty acids secreted in milk fat. This may give some inferences on differences in body fat mobilization between fat supplementation and non-supplemented cows. We're going to consider both total C16 fatty acids and total C18 fatty acids rather than the individual fatty acids to avoid the effects of biohydrogenation on what's actually absorbed. The data that I'm utilizing originated in a larger lactation study from several years ago in our group and represented control diets or fat supplemented diets. During weeks 4 through 25 of lactation, fat was supplemented through the use of whole raw soybeans, 10% of the total dietary dry matter, and 2.5% of a liquid fat, a grease type supplement. At week 26, the amount of fat was decreased through a small dietary change. The soybeans were removed from the diet and the amount of liquid fat was decreased slightly. This continued through week 43 of lactation. The milk fatty acid profiles were determined during week 3 of lactation, which was before the dietary treatment started, and then at weeks 7, 15, 23, 31, and 39 of lactation. We used intake and production data for the same weeks that we had milk samples, and then calculated the balances of fatty acids as digestible fatty acid intake minus milk fatty acid output. Some assumptions that we made in this analysis are shown here. Again, we're assuming that milk C16 arises half from de novo synthesis and half from blood lipids. We assumed constant digestibility of fat across lactation. The values we used were 72% digestibility for the control and 71% for the added fat diet. We also assumed that the fatty acid profile within the duodenum would be highly biohydrogenated and similar to that which we would find with the basal ingredients, and that was verified in a companion study to the analysis shown here. So we'll show several graphs in this format. We'll have the variable on the y-axis and the weeks relative to calving on the x-axis. Remember that week 3 was the 3rd week of lactation and before the dietary treatments were initiated. The control cows here are shown in the blue curve with the orange curve representing the fat supplemented group. This first figure shows the effects on dry matter intake, and you can see there was no significant difference in dry matter intake between control and fat supplemented cows across the entire lactation period. If we look at total fatty acid intake, however, that was increased markedly, almost, well over doubled in the fat supplemented group as expected. The amount of fatty acid intake decreased following the diet change after week 23. Milk yield also was not statistically affected by fat supplementation, although there tended to be a bit of interaction with slightly greater milk yield at peak for the fat supplemented cows and then a slight decrease later on in lactation. Body weight also was not affected significantly. You can see that the effects here are the body weight is higher for the fat supplemented group, but when we adjusted these using the covariate of the difference at week 3, the dietary difference disappeared. Now if we look at milk fat secretion, there was a tendency again for a diet by week interaction with milk fat output being greater at peak lactation than the non-supplemented group. Cows also maintained a slightly higher milk fat content through peak lactation compared with the non-supplemented group. Now if we look at the C16 and C18 fatty acid balances, it provides some differences here between the two types of fatty acid. So despite lower palmitate or C16 intake, total C16 fatty acid yield in milk actually was greater for the control cows than for the fatty acid supplemented cows. The C18 fatty acids in milk fat, however, showed the opposite effect. Fat supplemented cows had greater C18 fatty acid secretion in milk fat throughout lactation than the non-supplemented control cows. The calculated C16 balance then is much higher for the fat supplemented group than the control cows. You can see the differences here starting as early as the 7-week period of measurement and continuing on through the course of lactation. Likewise, C18 balance in the fat supplemented cows was substantially greater than the control cows, at least until the time of the dietary switch later in lactation. So some points to remember or think about these data. First of all, are the control cows really in a negative fatty acid balance throughout lactation? The absolute numbers here may be subject to errors in our assumptions or measurements, but regardless, the fat supplementation clearly improved the fatty acid balances for both C16 and C18 fatty acids. This implies either less mobilization and more storage of body fat in the case of the C18 fatty acids, or that we may have spared some energy in the case of the C16 fatty acid groups. Remember, these data were obtained for cows with a normal ratio of absorbed 16 to 18 fatty acids, and that may be different than when a pure fatty acid supplement such as a high C16 fatty acid is fed. The implications of this then are that in the presence of a normal duodenal fatty acid profile where there's a balance of C16 and C18 fatty acid, we did not increase C16 secretion in milk fat when there was more dietary C16 absorbed. Rather, the C16 synthesis seemed to be inhibited by this mixture of fatty acids. So a balanced fat supplement, that is one that provides both 16 and 18 carbon fatty acids, may then provide more benefits for energy and body condition store restoration than a pure C16 supplement. Some take-home messages. Obviously, lipid metabolism is a dynamic process across the life cycle and the lactation cycle. It seems that C16-0, palmitic acid in milk, may be a pivot point, as I'll call it, for changes in how mammary cells deal with fatty acid supply. For a supplemental fat that provides a normal mixture of C16 and C18 fatty acids, C16 may be decreased in its de novo synthesis in the mammary gland. The supplemental C18 fatty acids increase their output in milk and overall improve the body C18 fatty acid balance. So high palmitic acid supplements may increase milk fat content and yield, at least in cows in positive energy balance and perhaps lower yielding. Selection of fat supplements then should take into account both the stage of lactation and perhaps the differing metabolism of C16 versus C18 fatty acids. Thanks very much for your attention, and I look forward to addressing your questions.